Hi everyone, we are Team One. I'm Rosisha, and joining me are my four teammates Ashal, Kevin, Barnabas, and Sneha. Today, we are going to walk you through our project on insider threat detection. We will walk you through the problem we are solving, the architecture we have built, and how it works end to end. A quick demo, and then the results, trade offs, and where it could go next. When most people think about cybersecurity, they picture threats coming from the outside, hackers trying to break in. But some of the most damaging security incidents come from inside an organization, from people who already have legitimate access. These are called insider threats, and they are especially hard to catch precisely because the person is supposed to be there. So let's talk about why this problem is so difficult. The core challenges with insider threats is that they come from authorized users. A firewall or antivirus won't help you here because the person already has valid credentials and permission to be in the system. Traditional perimeter security is built to keep outsiders out. It isn't designed to question someone who's already inside. That means the only reliable way to catch an insider threat is to watch behavior. You have to look at what users are actually doing and ask, is this normal for this person or is something off? For example, is an employee suddenly downloading huge amounts of data they've never touched before? Are there dozens of failed login attempts on an account in a short window? Is someone logging in at 3 in the morning when they normally work 9 to 5? On their own, these might be harmless, but these are exactly the kinds of signals that can point to a compromised account for a malicious insider. The other problem is scale. A real organization generates an enormous volume of logs every single day, and no security team can manually review all of it. So, what's needed is an automated system that continuously monitors activity, detects anomalies, and alerts someone the moment suspicious behavior appears. To keep this focused, the system is designed for a single enterprise environment, one organization generating the logs, and one central monitoring system watching over them. That's where our solution comes in. We designed an event driven security monitoring pipeline built entirely on AWS, and here's how it works. User activity logs are stored in Amazon S3. The moment a new log file lands there, it automatically triggers an AWS Lambda function. There is no server running constantly and no manual step. The Lambda function reads the log data and analyzes it for suspicious patterns, excessive failed logins, unusually large downloads, or access outside normal working hours. When the system detects a potential threat, two things happen. First, the incident is recorded in DynamoDB, so there is a permanent record of every alert for later investigation. Second, Amazon SNS sends a real time email notification, so the security team is alerted immediately rather than finding out days later. The whole pipeline is serverless, which means it scales automatically and only runs when there is actually data to process. And it's modeled around a single organization, one company's employees, one set of logs, and one central pipeline analyzing them for insider threats. So, in short, this project shows how cloud computing and automation can turn raw activity logs into actionable security alerts while demonstrating core cybersecurity concepts like anomaly detection, log analysis, and incident response.
This architecture uses several AWS services working together. Amazon S3 stores the uploaded log files. AWS Lambda processes and analyzes the logs. CloudWatch monitors execution, and SNS sends alert notifications. Together, these services create a scalable and automated insider threat detection system. We begin by uploading a sample CSV log file containing user activity records to an Amazon S3 bucket. This simulates log data being collected from an organization's system. The file upload automatically triggers an AWS Lambda function which reads the log entries and applies our detection rules for failed logins, large file downloads, and after hours access. As the analysis runs, CloudWatch captures the execution logs, allowing us to verify that the processing completed successfully. When suspicious activity is detected, the system generates alerts and sends email notification through Amazon SNS. At the same time, incident details can be stored for future investigation and auditing purposes. Detection logic. At the core of our system is a rule based detection engine that analyzes user activity logs for behaviors commonly associated with insider threats. The first rule focuses on failed login attempts. If a user exceeds a predefined threshold of failed logins, the system flags the activity because it may indicate unauthorized access attempts or credential misuse. The second rule monitors file download sizes. Large downloads that exceed a specified threshold can be a sign of data exfiltration or unauthorized transfer of sensitive information. The third rule checks for access outside normal working hours. Activities occurring before 6 a.m. or after 8 p.m. are considered unusual and may warrant further investigation depending on the organization's policy.
Hi, my name is Barnabas Johnson, and I'm going to be presenting the outputs and the advantages of this project. So we needed to prove this actually works, not just in theory. We put together a test file with 200 rows of user activity. Out of those 200, we planted 31 anomalies on purpose, 14 large downloads, 9 failed login clusters, and 8 after hours access events. The rest were normal behavior. We uploaded that file to S3 and the pipeline ran on its own. No clicks, no manual steps. Within about 30 seconds, 31 alert emails landed in the inbox. Not 30, not 32, exactly 31. We cross-checked against the answer key from the test generator, and every single anomaly was caught. On top of the emails, DynamoDB had 31 incident records stored, each with a unique ID. CloudWatch logs confirmed 31 SNS publishes, so we had 3 independent verification points, all agreeing on the same number. 0 false negatives on the test set, and no false positives either, though that's partly because the test data was clean and synthetic. Real world data could be messier. Now, let's move on to the advantages of this system. The first thing worth calling out is that there is no infrastructure to manage. Lambda runs when it needs to and sits idle the rest of the time. During our testing phase, the AWS bill came out to a few cents. For a small or mid-sized organization that can't justify a full SIEM deployment, that cost model is hard to beat. Second, the event-driven design means detection happens automatically. Nobody has to remember to run a script or check a dashboard. The moment a log file hits the S3 bucket, the analysis starts. That removes the human bottleneck that causes most log data to go unreviewed in the first place. Third, every incident gets stored in DynamoDB with a unique ID. That matters for audit trails and for investigations after the fact. If something happens 6 months from now and you need to look back at what was flagged, the records are there. And finally, the whole system is modular. If we want to add a fourth detection rule tomorrow, say flagging access from unusual IP ranges, we just update the Lambda function. The rest of the pipeline stays the same. That makes it easy to evolve the system without rebuilding anything.
There are few limitations to our project that we have built, the whole workflow. The biggest one is that this is entirely rule based and doesn't have an AIML algorithm or pattern. It fires on fixed threshold like a download over a certain size. The problem is anyone who knows the threshold can just stay under it or exfiltrate out slowly over time. So no single event looks very suspicious, and because it's only catches patterns that we explicitly wrote rules for, a brand new technique that we did not anticipate can go completely unnoticed. And second false is false positive. A legitimate big download, say a backup job or an analyst pulling down a data set, looks exactly like an exfiltrate under a pure size rule. And when analysts get flooded with false alarm, they start ignoring alerts altogether. I also don't have a feedback loop to mark something as a false positive and tune it out in this workflow that we have built. Also, the third limitation is that every event is evaluated on its own. Real insider attacks are usually like a chain reaction, a failed login, then a success, then a privilege change, then a big download on their own. Each looks pretty much harmless, but altogether they look like an attack. Right now, the Lambda function cannot connect those dots because there is no session or a sequence analysis that we have built into this workflow. And finally, a limitation that is it's batch based, not real time. Detection only happens once a log file reaches or lands in the S3 bucket. So there's a delay between the actions and the alerts. And during an active exfiltration, those minutes of the whole process of uploading matters a lot, and it also depends on heavily on how clean and structured these logs are. If the format changes or fieldings go missing, the flow might break and we may not get any alerts. About a little bit of future enhancement that we can do in this project. To fix the rule-based problems, we would bring in machine learning using Amazon SageMaker to train custom anomaly models, or look out for metrics as a managed option. Instead of using static thresholds, the system would learn what normal looks like and can flag deviations. And building on that, we can also use behavior profiling, basically UEBA, where we build a baseline for each user, their typical login times, data volumes, what they normally access. We would pair that with Amazon Mazy to identify what sensitive data is being touched along with how much. And to solve the latency problem, we can swap the S3 batch trigger of for Amazon Kinesis. So events get analyzed in real time as they stream in, and also use Event Bridge for cleaner event routing. For the false positive, which we discussed in our last slide, instead of simple yes or no alert, we can move to a risk scoring model that combines multiple weak signal into one. We can then orchestrate with step function and even use Amazon Bedrock to summarize and translate alert in simple terms for the system analysts. And to scale it for a real organization, which can be one of the biggest enhancements, we would add multi-tenant support using AWS organizations to aggregate multiple accounts. I would also like to acknowledge that whatever we built, the end-to-end workflow for this project, for the insider threat detection, Amazon does a lot of it already and provides it as a service. For example, GuardDuty does ML-based threat detection, AWS Detective handles event correlations and investigations, and Security Hubs aggregate finding across all the tools and services that AWS provides. But we wanted to build this end-to-end simple workflow to understand the trade-offs and the reason why we need to choose a particular workflow over the other. For example, why real-time beats the batch processing, why behavioral baseline beats static rules. So we learned a lot along the way. So to wrap it all up, we have demonstrated a cloud-based insider threat detection. We took a real security problem, caching malicious behavior from people who already have legitimate access, and build an actual pipeline to detect it. As we see, the whole thing runs on AWS serverless architecture. There are no servers to manage. S3 receives the logs, Lambda runs the detection logic, SNS handles alerting, and DynamoDB stores the incident. It scales automatically and you only pay for what you use, and it's a very little operational overhead. Also automates security monitoring. Although in our pipeline we saw that there was one manual efforts that we had added, which is to upload S3 logs to the S3 bucket, but apart from that, everything else is automated. The system watches for the threat detection, fires and alerts, and the moment something matches, and records every incident automatically. As I spoke about this in my previous slides, for future enhancements, we can extend this to real enterprise for use cases, adding machine learning, real-time streaming, and behavior profiling, which AWS is already doing most of it. Thank you.